Welcome to The Free Will Show, a podcast that provides a beginner-friendly introduction to free will while also exploring cutting-edge developments on the topic. I'm Taylor Sear.
And I'm Matt Plummer. In this episode, we talk with Jeffrey Koperski about whether physics rules out libertarian free will.
Thanks for listening. Well, I'm happy to introduce Jeffrey Koperski, professor of philosophy at Saginaw Valley State University. Jeff is a philosopher of science and of religion, and he's written several works on physics and free will in particular, including a book called Divine Action, Determinism, and the Laws of Nature, published by Routledge in 2019, and a more recent book, hot off the press really, called Physics and Free Will, The Science of Libertarian Freedom. This was also published by Routledge in 2026, this year. And we're going to focus on material from that book in our conversation today. So welcome to the show, Jeff. Could you start by telling us a bit about yourself, your work, and how you came to be interested in working on issues related to free will?
Sure. Thanks, Taylor. I really appreciate the invitation. So like you said, I'm a philosopher of science. But unlike a lot of your guests, I think, I didn't start out in philosophy. So my bachelor's degree is in electrical engineering. Mm-hmm. As a freshman, I took exactly one course in philosophy. That was enough for me. I did not take any more philosophy as an undergraduate, tragically. But one topic I did find interesting was this whole question of determinism and free will. That one really bugged me. But when I did make the turn into philosophy in graduate school, I focused on philosophy of science, mainly philosophy of physics. So all of my early stuff was on chaos theory, for example.
Yeah.
I would talk about free will in my courses, but I never wrote anything about it. But over the last 10 or 15 years, I would periodically see a physicist say that given what we know about physics, free will is just impossible. And these are public-facing physicists. So they're people like Sean Carroll and Brian Greene and Sabina Hassenfelder. Yep. So they have a pretty significant audience. And since they're physicists, and most of whom have pretty impressive credentials, the press and other people, they give their opinions an awful lot of weight. Mm-hmm. But when you examine what they're actually arguing, I would say that the heavy lifting isn't being done by the physics at all. It's really done by philosophical assumptions, right. Things about reductionism and the causal closure of physics and what counts as real science. So these physicists, they tend to treat their views as just established scientific facts rather than the contentious philosophical positions that they really are. And these are the sorts of things that I've spent my career thinking about. So I knew that the physics alone entailed no such thing about free will. Mm. So about the fifth or sixth time I heard someone say that the physics rules out free will, I said, I'm going to write a book, which was a joke until it wasn't. Right. So here I am on your show. So the goal of the book, it was really to disentangle the science from the philosophy that I think has been grafted onto it. And once you do that, the alleged conflict between physics and free will, it largely dissolves. Mm-hmm. So let me be clear going in. I have no problem with the physics. So I've learned a lot from Sean Carroll over the years. I just wish that they'd stay in their lane. Yeah, right. So what I show is that the conflict is really not between physics and free will. The conflict is between free will and a certain philosophical approach to science, something that Bob Batterman calls fundamentalism. So fundamentalism says that all the real truths in science can be reduced to fundamental physics, at least in principle.
Yeah. Well, we're going to ask you about what physicists say, and you've already mentioned a few physicists and what they say about free will, and especially about the reasons for the skepticism about free will. But before we get to that, it would be helpful to lay out our key terms. Could you explain the sort of libertarian freedom you focus on, and also what sort of determinism is it incompatible with?
Good. So as your regular listeners know, libertarian freedom is fully caffeinated free will, right? So I often tell my students that it's the sort of free will you think you have until some philosopher or scientist talks you out of it. So more precisely, libertarian freedom says that our actions are caused in part by our own choices. And those choices are not fully determined by prior physical states and the laws of nature. So if I choose to sip my coffee before answering your question, that choice is in some critical sense up to me. And whichever way I do choose, I could have done otherwise. So my decision wasn't somehow determined by the laws of nature at some really deep level. So it's what experts in free will call leeway libertarianism. So the future has live options. After this interview, I might grade some papers, I might take a walk, and which way things go is at least partly up to me. Okay? And I should say, I'm not arguing, this is not a full court press for libertarianism. All I want to show is that physics hasn't refuted it. So figuring out whether libertarianism or some sort of compatibilism is true, that's your job. Okay. You guys are the experts on this. I just want to show that physics hasn't somehow settled the matter when we weren't paying attention. Okay.
Right.
So as you said, that the traditional foe of libertarianism, that is, of course, determinism. And there are several types. And what you usually hear about is physical or causal determinism. So in physics, when a system is deterministic, once you set the initial conditions, there is exactly one way that system can evolve according to the laws of nature. If you put the system back in the same initial state, it will evolve in exactly the same way. So if the universe itself is deterministic, once the initial conditions are fixed at the Big Bang, everything else is determined by its laws. Okay, that's just the classical Laplacian picture. So Laplace said that a superintelligence that knew all the laws and the state of every particle in the universe at a given instant could calculate the state of the universe at any point in time. So for that sort of superintelligence, what people call a Laplacian demon, nothing would be uncertain. So Hassenfelder herself says that the Laplacian demon, it could predict the next presidential election, for example.
Yeah.
Okay? And then I also have one chapter on what I call space-time determinism, and that comes from special relativity. So a lot of philosophers and physicists think that relativity supports eternalism in the philosophy of time. And that's the view that the past, present, and the future, that they're all out there, they're all equally real. So from a God's eye point of view, the whole timeline exists. And so what you think of as next Saturday, that's just as real as what's happening right now today, according to eternalism. Okay? And then the other thing is that nothing within the timeline can be changed according to eternalism. There's already a fact of the matter about what you're going to have for dinner next Saturday, and you can't change that fact. You aren't free to do otherwise. Now, everything I just said there, that's pretty much conventional wisdom when it comes to physics and determinism. But part of what I want to show is that a lot of the conventional wisdom is just wrong. Okay, so for example, we're often told that classical mechanics was deterministic, but quantum mechanics is not. But it turns out that determinism breaks down in classical mechanics as well. And that's not controversial in the history and philosophy of physics, but even most physics students aren't aware of that. For example, that story I told about the Laplacian demon, that only works in a world of point particles. So you can't tell that story if the world contains fluids or fields, for example. So even if classical mechanics were true, that would not entail that nature is fully deterministic. On the other hand, it isn't clear that quantum mechanics is indeterministic. So under the standard Copenhagen interpretation that we still teach to undergraduates, it's indeterministic, but it's not in the many worlds interpretation or Bohmian mechanics or several others that philosophers and physicists are familiar with. So while libertarians often appeal to quantum mechanics as a kind of refutation of determinism, it really depends on which interpretation is right. And there's no consensus right now about which one is true. So all that I just said about that's all interesting stuff. I've got a whole chapter on that, but I also think it's somewhat of a distraction when it comes to free will. So in my view, it actually doesn't matter whether quantum mechanics is deterministic or not. So in the book, I just grant that fundamental physics is deterministic. Now, you might think I just gave the game away at that point, but I think you'll see why I haven't.
Right. That's interesting. All right. Well, let's turn now to what the physicists are saying, or at least some of them. So in the first chapter of your new book, you survey several prominent physicists' reasons for rejecting free will. Could you give a brief summary of their case against free will?
Sure. So they have three main arguments, and they overlap a lot. So the first one is from Brian Greene, and his claim is that nothing in the physical world is outside the control of the laws of nature. So there are no events that transcend physical law. And then that applies to us, right? Because we're part of nature, and that means that we are as fully law governed as a clock, even if it doesn't doesn't seem that way. So we can talk about having free will. It's an illuminating story, as Green puts it, but it's not literally true. There's no room for libertarian freedom in a law-governed world. The second approach is explicitly reductionist, and this is Sabina Hassenfelder's argument. So first she says that persons are nothing but collections of atoms. And second, the behavior of the whole is dictated by the behavior of the parts, by the atoms themselves, and that these are just scientific facts. So she thinks there just really is no room for disagreement here unless you just want to deny the science.
Yeah.
Now, since our behavior is determined by the atoms that we're composed of, one could predict exactly in principle how we're going to behave from knowledge of the behavior of the atoms alone. Again, at least in principle. Like I said, Hassenfelder thinks that the Laplacian demon could predict the outcome of the next election. Mm-hmm. Now, I should say that phrase "in principle" it's doing a lot of work here. Okay, like sure. Can she derive the behavior of hemoglobin from quantum mechanics alone? Well, of course, in principle, right? Mm-hmm. I wish word processors would administer an electric shock whenever authors type that phrase, because it's usually a sign that something really important is being brushed aside. And I definitely think that's true in her case. The third argument is from Sean Carroll. And Carroll is one of the most philosophically sophisticated physicists out there. And he starts with what he calls the core theory. And that's basically the standard model of particle physics, plus a bit of general relativity. So the standard model, that's where you find quarks, neutrinos, and all those other exotic particles that you hear about from time to time. Okay? And so Carroll says the core theory is more or less complete. Now, he's not saying that physics is done. It's just that whatever we discover in the future isn't likely to change the core theory. At that level, we've got things figured out. And so any new stuff that we discover in the future, it just isn't going to change the core theory significantly. So then here's his key point. Based on what we already know, there's just no place for any new causal influences like personal choice. So physics already accounts for everything that can influence matter. And if that's right, there's just nothing left for free will to do. So here's a simple analogy. Whatever exotic particles we might one day discover at CERN, it's not going to change like the periodic table, right? So there's no new element that's going to show up between silver and cadmium. Silver has atomic number 47, cadmium is 48. There cannot be a 47 and a half. And that's the kind of thing that Carroll is saying, that given the constraints imposed by the core theory, there's just no room for free agents that can move stuff around. Mm-hmm. Okay? So those are the three main physics-based challenges to free will that I discussed. There's also that issue with relativity and eternalism that I mentioned, but really that's kind of a side argument in all this. The main problems are really about parts and wholes and the laws of nature. Yeah. Mm-hmm. And ultimately, given what we know about things at the smallest scales, free will at the macro level is just impossible. That's really what all three have in common.
Mm-hmm. Yeah. So one of your points is that these alleged conflicts between physics and free will rely on these philosophical assumptions. And one of these concerns immaterial souls. Could you explain the position known as mind-body dualism and tell us how that view might bear on the question of whether physics gives us reasons for being skeptical about free will?
Yeah, so this is one way out of the problem of determinism. It's not the only way I talk about in the book, but it is one way. So mind-body dualism says that we have both a physical body and a non-physical mind. So when I say brain, I'm talking about a physical organ. When I say mind, I'm talking about something non-physical. Okay, so according to dualism, the mind can causally influence the body. Like when I decide to raise my arm, something non-physical kicks off a chain of events in my brain and nervous system. And that's just standard interactionist dualism. It's what we all teach that in Intro to Philosophy. Mm-hmm. So how does that help the libertarian? Well, if the capacity for making free choices, if that resides in the mind, then those acts are beyond the scope of natural law. So physical determinism doesn't apply to non-physical stuff. That's one reason I think that libertarianism and dualism, that they often go together. But you can't stop there because there are two physics-based objections to dualism itself.
Yeah.
And I talk about both of those. So the first is the causal closure of the physical. That's the principle that every physical effect has a physical cause. So the physical realm is causally closed.
Right.
Okay? If that's true, then even if non-physical minds exist, they can't do anything in the physical world. Nothing from beyond the physical world can affect the physical world. So all the causal work on this principle is done at the level of physics, and there's really nothing left then for a mind to contribute. So causal closure undermines dualism. The second objection is based on the conservation of energy. So for a mind to influence a brain, it would have to be a source of energy. But conservation forbids the creation of energy. So even if minds exist, they can't causally interact with brains without violating a law of nature. So that's bad. This is what Daniel Dennett calls dualism's fatal flaw. Now, I argue in the book that both of these objections are actually pretty weak. First, the causal closure of physics isn't something you find in physics itself. There's no theory, there's no law that says physics is causally closed. Closure is a core doctrine within physicalism, which says that only physical stuff exists. But that's a philosophical claim. That's a philosophical position. Like I said at the beginning, it's important to disentangle the physics from the philosophy in all of this. And when you round up all the philosophical arguments in favor of causal closure, they're inconclusive at best. I mean, I think they sound pretty good if you're already a physicalist, but if you're not, they just really aren't very persuasive. Now, the objection from conservation of energy, on the other hand, I think that is interesting, but it also rests on a freshman level understanding of conservation laws. So we tell our students that conservation means that energy cannot be created or destroyed. And we tell them that it's a fundamental law, so there are no exceptions. Now, neither of those are true. First, there are exceptions. Conservation doesn't hold in cosmology, for example. So energy isn't conserved in an expanding universe. For technical reasons I will not try to explain. But Sean Carroll is really good on this point, by the way. But I have talked with people who have PhDs in physics, and they don't realize this. It's just not something that comes up, in their training. More importantly, conservation of energy only applies to closed systems. So that's a system that is not exchanging particles with its surroundings. So the brain is obviously not a closed system, like even from a purely physical point of view, there's blood flow, right? So conservation doesn't apply to brains. Now, I make that argument in a much more precise and technical way in the book, but it really all boils down to the same thing. Conservation laws have conditions, and if dualism is right, then those conditions fail. It's not that conservation of energy is violated. Okay, it's that the conditions for conservation to apply are not met. So the bottom line is that mind-body dualism would not violate conservation of energy. Just conservation doesn't apply to that sort of system.
Yeah.
So in the end, physics does not refute dualism. Now, dualism, it still has problems. Okay, so most philosophers don't like dualism. That's fine. I'm not making an argument in favor of dualism here, but dualism is compatible with physics. It's not compatible with physicalism, but again, that's a different beast.
Right.
And one upside is that dualism gives the libertarian a means to escape physical determinism. It's not the only one, but in the first half of the book, that's pretty much what I want to show.
Yeah. Yeah, that's helpful. And that's an interesting way to criticize some of the common arguments against dualism from physics. As you just said, though, a lot of philosophers and a lot of scientists too reject dualism. And you note that many of the reasons for skepticism about dualism and about free will stem from a reductionist approach to science. So the next question is, what are some of the forms of reductionism that you have in mind?
Yeah, so the reductionist approach, it's not just a problem for dualism, as we'll see. It'll be in conflict with another approach that I'll get to. And I should say this is where things get messy because people use the word reductionism in a lot of different ways.
Yeah.
So Hassenfelder treats reductionism and physicalism as if they're the same thing, and they're not. Physicalism, it's an ontological claim. It says that the only things that exist are made up of the stuff recognized by the physical sciences. So it's an ontological claim. It's a claim about what there is. I should say there's some controversy about characterizing physicalism that way, but that's a good first approximation. Reductionism is different, and I distinguish two very broad types. So epistemological reduction is about our representations of nature and things like theories and models, the stuff you see in the textbooks. And so this sort of reductionism says that a theory at one level can be derived from a theory at a lower level, at least when you can reduce one to the other. So, for example, you hear that thermodynamics can be reduced to statistical mechanics. That's a claim about the relation between those theories. Ontological reduction is about the things themselves, not our representation of those things. So the naive version says X is nothing but Y. So an organ is nothing but a collection of cells, and mental states are nothing but brain states. The more careful version says higher level properties are determined by lower level properties. But epistemological and ontological reduction, those can come apart. So you can be an ontological reductionist and believe that every physical thing is ultimately made up of subatomic particles, but you might reject epistemological reduction, maybe because you think you just aren't smart enough to see how everything fits together. Yeah. So we'll never be able to fully reduce, say, psychology to neurophysiology because just maybe the brain is just too complicated. Okay? So the two can come apart. But the free will skeptics that I'm talking about, they actually accept both. They're what Batterman calls fundamentalists. They think that good explanations always point downward toward smaller and smaller scales. So disciplines like biochemistry and cell biology are just useful descriptions of systems that are really just collections of atoms. So most of what I'm doing in the last part of the book is challenging these fundamentalist assumptions. I don't think biology just is chemistry, or that chemistry just is physics. I think that emergent properties at higher levels are just as real as fundamental physics. Now, why think that? Well, one reason is that the fundamentalist approach itself has failed. You start to appreciate this when you look more closely at their best examples for reduction. And so let's just take one that everyone's familiar with. We're told that temperature just is the average kinetic energy of molecules. Well, that's true for ideal gases at equilibrium. But that's a very special case. Okay? That's not true for solids. It's not true for liquids. It's not true in space. And to get anything like the reduction of thermodynamics to statistical mechanics, you have to assume the system has an infinite number of particles. That's not just a handy idealization. I mean, the math literally does not work without that. And this is the sort of thing that it's true for all of the key examples of reductionism. When you look at them closely, they're all about special cases or limited domains or idealized systems. And from there, the fundamentalist claims that the full reduction is possible in principle. Right? After you've seen that move a few times, it really does start to look like all the important work is being done by the in principle part. And this is why you hear philosophers of science these days talk a little bit less about reduction and more about emergence. The reductionist approach only gets you so far.
Yeah. So you're telling me every time I'm teaching philosophy of perception and I use that example that heat just is molecular motion or kinetic energy that I'm wrong. It only works for ideal gases. I always use the example of like a frozen burrito and it's a solid. So you're telling me solids don't work.
It doesn't, it isn't the vibrations of the atom. Yeah, it doesn't boil down to just that.
All right.
So,
okay.
That's okay. I mean, you're not the only one because we just ignore all the qualifications. We ignore, all the stipulations of that and then just feel free to use it for everything else.
Yeah.
So, yeah.
All right. Well, so if we don't take a reductionistic approach, this leaves open to the possibility of other kinds of views like emergence. So could you explain the sorts of views that get categorized as emergence views and say how they're not reductionistic?
Yeah. So let me first say, for those listeners who don't like dualism, what I'll be marching toward is the view that emergence provides a different sort of grounding for free will. But again, emergence, it's another messy term. So as a first approximation, it's just the denial of fundamentalism. So the emergentist does not believe that higher level phenomena can be fully explained in terms of more fundamental theories. But the details, it depends on what type of emergence we're talking about. So when most scientists use the term, they're usually talking about what most of us call weak emergence. And so that's mainly the idea that at each level of complexity, entirely new properties appear. It's what Philip Johnson says, as he put it in a paper in the 70s that everybody quotes. He's a physicist, Nobel laureate. He said, more is different. More is different. So while atoms aren't viscous, fluids are. Lots of atoms together make a viscous fluid. And while organic molecules aren't alive, bacteria are. And so in addition, for weak emergence, you can't predict the emergent behavior from what we know about the base level alone. So we know a lot about atoms, but that won't tell you, the physics isn't going to tell you that evolution would one day produce penguins. Okay. Biology as a discipline is just largely independent of what's going on at the level of microphysics. I mean, look, penguins are made up of atoms, all right? But we just don't know the details about how one level gives rise to another. So weak emergence is emphasizing just our own epistemic limitations about how to fit everything together. At the other extreme is strong emergence. This is Tim O'Connor's view. Yeah. Unlike weak emergence, this type has to do with ontology. So it says that genuine causal powers come into being at higher levels. There's a kind of ontological novelty and autonomy at the higher levels. And these new properties are irreducible, even in principle. So consciousness is the standard example here. Strong emergence says that the reason we can't explain consciousness in terms of neuroscience, let's say, is because consciousness isn't just a brain thing. Consciousness depends on the existence of brains, but it can't be ontologically reduced to brain states. So strong emergence says that something new and fully real has come into being. Now, I think it's an interesting idea. It's not very popular, mainly because it leaves the relation between the levels as something of a mystery. Like, why does consciousness emerge from brains but not from clouds? Yeah. Well, it's kind of hard to say because we just don't have many good examples of strong emergence. Right. So most scientists and most philosophers of science tend to shy away from it. But between those two extremes, the weak and strong emergence, now this is where things have started to fill in, and this is where I think things get interesting. So one thing here in the middle is what Robert Bishop and Michael Silberstein call contextual emergence. And so they show how macroscopic properties, macroscopic behavior, is usually not wholly determined from the bottom up. And so the environment often has a key role. So here's one of Bishop's examples that he told me years ago. In a school of clownfish, if the dominant female dies, one of the males in the group undergoes a change of sex. Now, that's kind of amazing in its own right, okay? But here's the thing. What causes the change is a macroscopic property, right? It's the fact there is no dominant female in the school. And that fact about the school brings about changes at a lower level, at the level of cells. It's the group level fact that matters, not something at the level of chemistry or physics. And they just have a whole book full of examples like this. And what it shows, what contextual emergence shows, is that what's going on at the level of physics does not determine everything else. And that's directly contrary to the fundamentalist approach.
Yeah.
That's interesting. So there's weak emergence, strong emergence, contextual emergence. What sort of emergence view do you endorse? And what's the case for accepting the view?
Yeah, it's in the ballpark of contextual emergence. It might even be a type of contextual emergence. Bishop and I are still talking about that. I call it moderate metaphysical emergence. And so that puts it in this middle ground between weak and strong. It's metaphysical, so it is a claim about reality, but it's also less mysterious than strong emergence. So the case that I make for it is mainly, it's not philosophical, it's mainly scientific. I think you might be able to make a better, stronger case, more persuasive case for it using biological examples, and I give a few of those. But in the book, mainly I focus on physics. And that's because the free will skeptics I'm trying to answer, they tend to dismiss higher level sciences. But if you can make your case from physics itself, then the critics can't just wave it off. Now, as you imagine the physics side of this, it gets a little hairy, but let me try to give you a sketch of what I'm trying to show. So one thing is what physicists call universality. And that's just the fancy name for the fact that systems with completely different micro constituents can exhibit the same macroscopic behavior. So phase transitions are a good example. Everybody knows about the three states of matter, right? And so when a solid becomes a liquid or a liquid becomes a gas, that's a phase transition. And it turns out that magnets also undergo phase transitions, but those have to do with how the material becomes magnetic. And the surprising part is that the same equations apply to both types of phase transition. Now, again, that should be surprising because the magnet and say an ice cube, they have completely different microstructures.
Mm-hmm.
Right.
So how is it that the same equations describe the behavior of both, right? Why do things with different microstructures behave the same way at the macro level? To answer that question, that the answer can't have anything to do with what they're composed of. It's not about the microphysics, because whatever you want to say about the ice cube isn't going to apply to the magnet. They're just composed of completely different things.
Mm-hmm.
So if you want to explain their common behavior, you can't appeal to their composition. The composition, the micro composition is just irrelevant. The explanation is going to be found at a higher level. So here's a simple example. Maybe I should have started with this example. This is from Hilary Putnam. So he said, think of a block of wood with a 1-inch round hole. And you got two pegs. You got a round peg, you got a square peg. The round peg fits in the hole, the square peg does not. Why not? Well, not because of the composition of the board, because you'll get the same result if the board were steel or plastic rather than wood. So the explanation has to do with the geometry of the board, and that's a macroscopic property. The micro details here are just irrelevant. And the same idea shows up in a much more technical area in physics, something called condensed matter physics, that has to do with the behavior of solids and liquids. And researchers in this area often use a mathematical method called renormalization. And renormalization, it tells us, I'm not going to tell you how it works, just what it tells us in the end, when you turn the crank, is which properties matter in these systems and which ones don't, which properties are causally relevant for some behavior and which ones aren't. And what it shows is that the micro properties, they often just don't matter. It's like the peg and board example. The micro details, they're irrelevant. And what matters for the behavior of these systems are higher level properties. So it's kind of like the clownfish example, but now we're talking about physics.
Yeah.
Mm-hmm.
And this is directly contrary to that fundamentalist approach, which says that all behavior is ultimately determined by fundamental physics. It is not. And renormalization shows that. And then finally, I talk about multi-scale modeling in engineering. So when you model the behavior of something like a bar of iron under stress, you might think, well, we could just model that from, start with the behavior of the atoms and just, work our way up. It turns out it doesn't work. And it's not because we just lack the computational power to do it. That the behavior of the bar depends, again, on mid-scale properties that causally interact with properties at both higher and lower levels. So there are emergent properties at many levels between the atomic level and the macroscopic level. And if you ignore those properties, your model fails at some point. Now, why? Well, because those properties causally contribute to the whole. They aren't just convenient descriptions of some underlying atomic reality. They're genuine features of the physical world. And no purely bottom-up approach can capture that.
Yeah.
So, in other words, the reality of emergent properties has forced engineers to incorporate them into their models. So, if you take all this together, I would say all renormalization, multi-scale modeling, they give you physics-based reasons to think that emergent properties are doing real causal work, and that there's far more to physics than just the standard model. Okay, at the very least, it shows that fundamentalism should not be treated as the default position.
Yeah. Okay, so if one accepts your view of emergence, how does that help answer the problems that you pointed out at the beginning for physics and free will?
Yeah, so this is the payoff for all the technical stuff we just waded through. The critics who I discuss argue there's no free will because there's no room for it in fundamental physics. And in one sense, that's right. So you won't find anything like a free will force in the standard model. So I grant that. What I don't grant is their fundamentalism. Okay, so biological systems cannot be fully reduced to fundamental physics, even in principle. Not even condensed matter systems can be fully reduced to fundamental physics. The mistake is thinking that fundamental physics is the only level where real causal work happens. And what emergence shows, based on physics itself, is that higher level systems can have causal rules that are irreducible to the micro level. So you don't see those properties in fundamental physics because that's not the scale where they operate. So then this is the key move. Even if fundamental physics is deterministic, it doesn't follow that everything at higher levels is as well. The micro doesn't wholly determine the macro. Now, Christian List, who you had on your show previously, he argues the same thing. But what List needs, in my opinion, is an account of emergence to show like how it's possible, how it works. Yeah. And so I see myself at the end of the book as supplementing List's overall approach. And so I want to argue that free will is a real emergent capacity. Details are in the book, right? And I have to admit, if you want to connect all the dots, we would first have to fully understand consciousness, which we don't. Okay, so I can't get you all. I can't get you all the way. There's going to be some gaps here, but my conclusion really is quite narrow. All I want to show is that there is room for libertarian free will, given what we know about physics, and that's because there's more to reality than what physics describes. And the reason some physicists reject emergence is that they aren't considering the whole of physics. So it's like that proverbial drunk looking for his car keys under the lamppost, right? Because that's where the light is. They look at fundamental physics, they don't see any evidence for free will there, and they conclude it doesn't exist. But they're looking in the wrong place. And that's because their philosophical assumptions tell them that there is no other place that they need to look, because all the good stuff's happening down at the lowest level. Once you accept that physics allows for metaphysical emergence, their assumptions about reductionism pretty much lose their force. So the real issue here at the end of the day, the real issue, it isn't physics versus free will. It's whether you accept a strict form of reductionism that says only fundamental physics tells us what's real and what's causally effective. Again, that's fundamentalism. And the case I make in the book is that physics just doesn't, the whole of physics just doesn't support that view. In fact, the physics often points in the opposite direction. So once you separate the physics from the philosophy, the conflict with free will just largely disappears. Now look, libertarian free will, it still might be false. Okay, that's your expertise. That is not mine. Okay, but it's just not something that physics has ruled out.
Yeah.
Well, that's a helpful way to summarize the project of the book. Thanks for talking through it. If listeners want to check out the book, can you remind us the title and the publisher, and then also where else can listeners go to follow your work, Jeff?
Good. So again, the new book is Physics and Free Will. Physics and Free Will. It's published by Routledge. And I am on all the usual academic platforms. So for philosophers, Phil Papers, ResearchGate, academia.edu. Yeah, all my preprints and anything else I'm allowed to put up there is there.
Yeah, very cool. Thanks again for joining us.
Well, thanks for the invitation. I'm very, very happy to be here.
Yeah. Our next episode, we will talk about self-prediction, time travel, and free will. And our guest will be Alison Fernandez, Associate Professor of Philosophy at Trinity College Dublin.